right. Woo-hoo. Okay, now let's talk about Chapter 5. Let's talk about Chapter 5. All right, what is Chapter 5 about? Chapter 5 is about energy. Okay, so, gosh, what are we using energy for? Everywhere, like where? What are you guys using energy for? Study. Study takes a lot of energy. Take an exam. Yeah, exactly. Exactly. What else? What else are you using energy for? Running, work, yeah. What? Everything. Lights in here, right? Computers, your batteries. Where do you think you're getting the energy from those batteries? That's a chemical equation going on in there, reaction happening. That's where you're getting your electricity from. So, yes, we're using energy to light our homes, heat our homes. You know, that's a combustion reaction. How about that? Those Bunsen burners in lab, ooh, that's combustion reaction. Heat our homes, yeah. Fire up that gas grill, yep. All of those things, we use energy like, gosh, everywhere, all the time. It's such a huge topic. So that's what we're going to talk about in Chapter 5 is energy, and it's very important in the chemistry world and in our world around us because that's how we get so much of our energy is through these chemical reactions and things that are happening. So first off, we have to decide, hey, what is energy? Okay, so energy is the ability to what? To do work or transfer heat. So I'm going to say energy, we're going to give that a capital letter E. Energy is equal to Q plus W. Now W stands for work, right? Q, small lowercase q, is going to stand for heat. It's not going to be H, it's going to be Q. Q stands for heat, W stands for work. So energy is the ability to do work or transfer heat. Okay, so energy is the ability to do work or transfer heat. Now, you guys know what heat goes, right? Heat is the flow of energy. Which way does heat flow? From hot to cold or cold to hot? Hot to cold, right? And then when they get to the same temperature, the energy doesn't flow between them anymore, right? So that's what heat is. Heat is the actual flow of energy. So once they're the same temperature, we don't say it has heat anymore. There's no more flow, right? If two objects are the same temperature, we don't say one has heat and the other one doesn't. Okay, heat is the flow of energy. All right, so we know that, hot to cold. And of course, you know what work is. Like if I pick up a book, doesn't that take work to lift it in a gravitational field, right? Okay, so we know what work is. Work is you have to move that in like move an object or a mass. So we know what energy is. Now there's two kinds of energy. You guys familiar with the two kinds? We've already talked about kinetic, right? What's kinetic energy? Energy of motion, that's right. So that's one, kinetic energy. What's the other one? Potential energy. What's potential energy? What's potential energy? It's stored energy. There you go. It's stored energy, isn't it? You have potential. It's stored energy. Like if I lift the book up, it has potential because what happens if I let it go? It's going to fall, isn't it? Okay, so, right? Isn't that what's going to happen? Pick up a book, I let it go. Okay, so when you pick the book up, it has potential energy. There's two forms, potential and kinetic energy. Now, there are other kinds that we've heard of, chemical energy and thermal energy and radiant energy and solar energy and thermal energy. All those energy types are forms of potential or kinetic energy. Now, energy is transferred from one thing to another. We transfer energy back and forth. We can't create or destroy it, but we can transfer energy. So let's talk about an example of transferring energy. Okay, so here we go. It's a raw egg. So let's see what energy is involved with this egg. So, yeah, I know. I hope I don't miss. It would be a problem. Let's see. Okay. What does the egg have as far as energy goes right now? What would you say? Potential. Okay, tell me what happens. Where'd it go? Kinetic energy? So it transferred from potential to kinetic? Then where'd that energy go then? What happened? What? Chaos. I broke the egg, right? Well, doesn't that take work to do that? Oh, yeah, yeah. So energy is just, you see the energy change from one thing to another to another? Sure, it went from potential energy to kinetic energy, and then we did some work, because energy is heat or work, right? So energy is transferred from one thing to another. Okay, we can't create or destroy energy. We just transfer that back and forth around. Now, we have to talk about the units of energy, and we're going to use joules and calories. So a calorie, what's a calorie defined? That's defined as taking 1 gram of water. Okay, 1 gram of water is like about this much. It's itty bitty. 1 gram of water, and you're going to raise that 1 degree. Okay, that's not very much, right? That's a tiny amount of energy to do that. So that's a calorie, is the amount it takes to raise 1 gram of water just 1 degree. Now, there's a nutritional calorie. You've probably heard of the calories that you read on the back of the label. Okay, that's a different kind of calorie. I know they're spelled the same, but we're going to denote the difference by a capital letter C. Capital letter C is equal to 1,000 of our little chemistry calories. Okay, so 1 nutritional calorie is 1,000 chemistry calories. All right, so that's not the same as what's on the back of those labels that we're reading. We're talking about a different calorie. Then the other one is a joule. A joule is 4.184 joules is in a calorie. So if a calorie is tiny, what does that tell you about a joule? It's even smaller. Okay, it's very, very small. And we might have heard of kilowatt hours. When we talk about 1412, we'll get into kilowatt hours. And this is to kind of give you a perspective of like the numbers. So you can see joules and calories are small units. So when you're doing that experiment lab with calorimetry and you're like, this is a gigantic number, thousands upon thousands of calories in joules. Yeah, it's going to be a big number. Okay, and then this is kind of how much energy it relates to. So 100 nutritional calories is how much it takes to run a mile. So I'm thinking, that's all? It feels like a lot more than 100. And then here's how much energy we use in an average day, which is an awful, awful lot. We use a lot of energy. Okay, so those are the units of energy that we're going to be talking about. Another thing that we need to talk about with energy is we need to define the system and the surroundings. Everything has got all kinds of energy going on, but what we want to focus on is the system, the energy of the system. The system is like what's happening. Maybe this is a reaction of the system, like barium hydroxide, ammonium nitrate, you know, that's the system. Well, what's the surroundings then? Everything else. Might be the water, okay, the flask, the air, the tables, the chair, the building, the town, the country, the world, and so on, right? Okay, so the system is what we're focused on. And a lot of times when we're talking about energy, we're always in the surroundings because you're never inside that flask. You're always part of the surroundings. So you have to be very careful because when we think of this stuff, we have to be thinking of it as if we were inside the flask. Okay, you have to look at it from that perspective of the system. So then what we're saying is the energy, okay, so can't we say the energy of the universe is equal to the energy of the system plus the energy of the surroundings, right? Okay, so energy of the universe is equal to energy of the system plus energy of the surroundings. That makes sense, right? And what we want to focus on is the energy of the system. Okay, well, that's sometimes kind of hard to measure, the energy of the system. We're like, well, what is the energy? Well, I don't know. You got kinetic energy, the electrons are moving around, you got potential energy in there. It's like, ooh, that's kind of hard to measure. So it's much easier to measure if I take the change as well. Change in energy. That's a little bit easier for me to measure, is the change in energy. And as we talk about the change in energy, how do we define change? Change, you guys remember change is defined as final minus initial. Change is always defined as final minus initial, and there's a little triangle. So that's going to be E final minus E initial. Okay, now we're talking about the energy of the system. I'm talking about a change in energy of the system. Well, if the system is changing energy, wow, where's it going? If the system is losing energy, where's it going to go? It's going to have to go to the surroundings. If the system is going to gain energy, where's it coming from? The surroundings. Okay, so what we're saying is that we're going back and forth. If a system loses heat, it goes to the surroundings. If it gains heat, it's coming from the surroundings. Same thing with work, because energy can either be heat or work. So energy and work goes back and forth between the system and the surroundings. Well, if it's just changing back and forth between the system and the surroundings, doesn't that mean that the energy of the universe is not going to be changing? It just shifts back and forth between here. Okay, so that brings us to our first law of thermodynamics. There are 3 laws of thermodynamics. We're going to learn the first one now, pick up the other 2 later. The first law of thermodynamics is energy is neither created or destroyed. Remember, we just changed it around. So we can't create or destroy energy. All the energy we've got is what we've got. All we can do is shift and transfer and change it around. So the energy of the universe is going to be constant. Okay, so the energy of the universe is constant. That's your first law of thermodynamics. And we're going to learn some other ones. Okay, so what's the first law of thermodynamics? Energy is what? Okay, very good. It's neither created nor destroyed. And the energy of the universe is constant. Okay, and this is, we can understand how to shift energy from the system to the surroundings in form of heat. That's easy. But how do you do work? Well, this is an example of work, of a system doing work on surroundings. You have a combustion in the piston, and it moves that, or in the chamber, and it moves the piston up, so it did work on the surroundings. So we can do work on the surroundings, work on the system. Energy to the surroundings is heat coming into the system. All right, let's talk a little bit more about this. Energy of the system is final minus initial. Okay, so if I have a positive change in energy, which one was bigger, final or initial? Final. So what does that mean? That energy, if the change in energy is positive, so that means E final is bigger, right? So what did that mean? Did energy come into the system or leave the system? If it's bigger, that means it had to gain energy, right? And it gained energy from where? The surroundings. Okay, so we're talking about the system, remember? So E final is bigger, so that means the system gained energy from the surroundings. Okay, well, what if it's negative then? What is that saying? Which one is bigger? Okay, E initial of the system is bigger. So if it was bigger to start with, what happened? Lost energy to? Good. So the system lost energy to the surroundings. Okay, good. All right, I've got the flasks here, so I want you to tell me which way the energy went, and we're going to talk about energy in the form of heat. So which way did it go? Which one of these did the system, and we're talking about the system as what's in the flask, so you have to decide, did the system gain energy or did the system lose energy? Okay, so this has all been sitting here for a while, and it's been at room temperature, so let's put this together, and then let's see what happens. Okay, so we're going to have to move these rather quickly because as we're talking about losing heat or gaining heat, it's going to go fast. So feel the bottom, pass that around, move it along before it loses its heat. Okay, we'll start that one here. Okay, so feel it, pass that around. Anna? Okay, so that's a good question. We have to think about that. Which way did it go? So you can feel it when you feel both of them, you could probably get a better idea of what is what. Okay, so you remember we're going to be talking about this from the perspective of the system, not the surroundings. You're part of the surroundings. You've got to be the solution, right? Yeah. You feel this one, yeah? Yeah. Okay, so everybody felt this one, yeah? Okay, this is the ammonium nitrate. So did you guys all feel this one? Okay, so yeah. All right, did you feel this one? Maybe you didn't feel that quite well. Did you feel that? Yeah. Yeah.
What's the difference when it first started?
Oh yeah.
Now it is.
Yeah, so if you could feel it now. I don't know if does it feel warmer, yeah? Okay. All right, so let's talk about that. Did you decide which is which? Which one you want to talk about, the sodium hydroxide or you want to talk about the ammonium nitrate? Sodium hydroxide. Okay, let's talk about this one first. How'd that feel? Felt warm. Okay, woo, I don't even have to touch it and I can feel the heat. Okay, so think of the perspective of the system, which is inside the flask. What's happening to the energy with that system? Is it leaving the system or going into the system? It's leaving the system. Energy is leaving the system, okay? It's in the form of heat, isn't it? So we say energy is leaving the system. And we could say it's exiting the system. So if heat is exiting, we're going to call it exothermic. Yay, exothermic. Isn't exiting, leaving, that's like negative, right? It's like taken away. So exothermic then, leaving the system, is going to have a sign of what? Negative. Okay, so if it's negative, then it's exothermic. So this one is exothermic, negative. So what happens in an exothermic reaction? What is energy doing? It's what? Leaving the system, but going into the surroundings. Okay, but we're leaving the system, so it's negative. Now, if I put a thermometer in here, what would you anticipate the thermometer temperature to do? What? What would it do? Go up. It goes up because remember the thermometer is the surroundings. And I stuck it in the system. So the energy is leaving the system and going into the thermometer and heating the thermometer up, and that's how come the temperature's rising. Okay, well let's talk about this one, ammonium nitrate. How'd this one feel? Felt cold. Oh, so you touch it and it feels cold. Wow, what's happening? Energy from where? Surroundings. And so what's my hand then? Is that surroundings? So you can feel it's cold. Why do you feel it's cold? Because it's like, heat is leaving my hand. That's why it feels cold. And where's the heat going if it's leaving my hand? Into where? The system. That's right. So my hand was the surroundings and it's going into the system. Okay, so we're going to say energy into the system in the form of heat into the system is going to be coming in. So guess what we're going to call it? Endothermic. Yay! Okay, so this one's going to be endothermic. And what is the sign of endothermic then? Positive. Exactly. Okay, so endothermic is heat coming into the system. All right, heat into the system. Now, we can say another word for final minus initial if I'm talking about a reaction. So here we have reactants forms products. Okay, so reactants forms products. So what would final be? Final would it be the reactants or the products? Products. So I can take off final and put products here. And then initial would be the reactants. Okay, so products minus reactants. The energy of the products minus reactants. That's how we're going to talk about energy of our chemistry equations. Okay, so it's products minus initial. All right, does that make sense? Okay, now as we talk about energy in the form of heat, we can also talk about work, the signs of work. Same thing. Because we said energy is equal to Q plus W, right? So let's talk about work. What are the signs of work? Now, if the surroundings is doing work on the system, I bet you can tell me what the sign's going to be. Positive. Isn't it coming in? Yeah, it's like our endothermic, isn't it? So work done by the surroundings on the system is going to be positive. How about work done by the system onto the surroundings? Negative. Okay, be careful of that. Work done by the system is opposite of work done on the system. Okay, so work done by the system onto the surroundings is negative, right? Okay, awesome. So let's put this problem up here and see if you can tell me what is the total energy involved here, taking into account work and heat and the correct signs. Okay, so I'm not going to put the signs up here because I want you to think about it. If I have a gas, let's say I have a gas, and it absorbs, okay, I'm leaving off the signs because I want you to think about this, 155 joules of heat and does 79.9 joules of work on the surroundings. Okay, so what then is the total energy? And remember, E equals Q plus W. It's not going to be 200 something. Nope.
75.1.
It's not going to be 200. No. Nope. You got to think. It's going to be what? 75.1. Wow, joules. Perfect. Why is it going to be 75.1? Why is it not 200 something? Ah. What did we say? Gas absorbs. So it's positive. This one's positive. Absorbs, right? Coming in. Okay, so this one's going to be positive. Positive 155 joules. And what about this? The system does work where? On the surroundings. So what's the sign then? Negative. That's negative, right? Did we follow that? Okay, has everybody got that? All right, and so then you can calculate the energy, and it is a positive 75.1. Okay, so we can all do the signs of Q and W? Yes. Okay. Awesome. Awesome. Well, now that we understand this, let's talk about what is a state function. That's the next thing we want to talk about. Since we understand that, we can introduce another physical property, and that's a state function. What's a state function? A state function is going to be independent of how you got there. All we care about is final minus initial. I don't care how we got there. That's an example of a state function. Energy is a state function. That's why we can say final, whatever the final energy is, minus whatever the initial energy is, and that's going to be the change in energy. It doesn't matter to me how I got there. So let's take a look at this picture. How is this going to relate to that? Well, this is an example of what a state function is. Here's campsite 8 at 1,200 feet, and there's campsite B at 4,800 feet, right? Okay, the difference between those two is going to be the same, right? But what if I took a straight pathway from campsite A to campsite B? I'm still at altitude 1,200 feet, and I'm still going to be at altitude 4,800 feet, right? Straight there. Still same campsites. Well, what if I didn't take the straight pathway and I took the long, windy road? Doesn't matter. I'm still going to be at that difference. So final and initial, doesn't matter how I got there, it's the same. That's an example of a state function. But what is an example of something that's not a state function in this picture? Where it does matter which way you go. Yeah, the distance. Is the distance different between these two? Yeah, that's something that's not a state function. Okay. But the example of the altitude is a state function because it doesn't matter which way I take it. I'm still going to get to the same spot. Does that make sense of what a state function is? So a state function is independent of the pathway. That's what we're saying. State function is independent of the pathway. So E is a state function for energy, and we're going to denote the state function by a capital letter. So you know why we said E is a capital E and not a lowercase? Because we're saying it's a state function. But notice that we did Q a lowercase. So what does that mean? It's not a state function. Lowercase means it's not a state function. So W is also lowercase. So what can you tell me about W? Is it a state function or not? No, it's not. Okay. Well, now that we understand state functions, we're going to introduce another idea that's a state function, and that's enthalpy. Okay, so state function is independent of the pathway. Right? State function is independent of the pathway. So let's introduce another state function. We already said energy was a state function. Q and W are not. So let's introduce another state function, and this one is called enthalpy. Enthalpy. Okay, so that's E-N-T-H-A-L-P-Y. Enthalpy. Okay, now this is a state function, so we're going to abbreviate that with the symbol capital letter H. So when you see H, you're going to think it's enthalpy. Are we going to think it's heat? No, H is not heat. H is enthalpy. Well, what is enthalpy? Oh, okay. Enthalpy, gosh, it's kind of hard to think about what enthalpy is. Enthalpy is the energy of the system. Energy of the system plus pressure volume work. Okay, it's the energy of the system plus pressure volume work. That's what enthalpy is. So that's kind of hard to get our head around. PV, pressure volume work. P is pressure, V is volume. That's pressure volume work. So energy of the system plus pressure volume work. And that's kind of hard to get our head around. So a way that enthalpy becomes more useful to us is if we think about pressure volume work. Well, what if we're under constant pressure? So let's say you're in the lab and you're working on this experiment. Are you under constant pressure? So besides to get it done, right? You're like, I'm under pressure to get it done. I got to do a good job. Besides that pressure, are you under maybe, say, atmospheric pressure? Yeah, are we all sitting here under atmospheric pressure? Yeah, so the reaction is happening under constant atmospheric pressure. So at constant pressure, okay, so at constant pressure, what happens in this equation, knowing that E equals Q plus W, then what happens is enthalpy equals Q. So now we can say, oh, the heat of that reaction is the enthalpy of that reaction. And that's where sometimes we get kind of confused and why some people think that H stands for heat. It doesn't. It stands for enthalpy. But under atmospheric constant pressure, enthalpy is heat. So this is what becomes useful to us. So then we can measure the heat of the reaction and say, hey, that's the enthalpy. Enthalpy is equal to Q. But when this only happens under what conditions? Yeah, constant pressure. Now, it's a state function. So what did we say a state function was what? Independent of how we get there, right? So does that mean I can have a final minus initial? I can. So we can have the change in enthalpy is equal to the enthalpy final minus initial. And we know final is another word of saying products minus enthalpy of the reactants. Okay? So that's what we can also do. And that we can tie to our equations and our reactions. So if you have this situation where heat Here you have lower energy, and it got to be higher energy with the products. Well, the only way I'm going to go from lower to higher is, didn't I have to gain energy? Gain energy from where? Surrounding. So energy's into the system. So what is that? Endothermic or exothermic? Endo. And what's the sign? Positive. So there we go. And then the same thing for the other way. Right? If we started out higher energy with the reactants and we lost energy with the products, energy had to go somewhere. So it went out to the surroundings. So it goes out to the surroundings. So what's the sign then? Negative, and it's called exothermic. Yay! Awesome. Right? Good? Okay, so we understand now what energy is, don't we? And we understand now what enthalpy is, right? And so what can you tell me about enthalpy so far? What do you know about enthalpy? It's, yeah, it equals heat where? When? Constant pressure, and it's also what kind of function? State function. So you know those two things about it. And that enthalpy is defined as energy of the system per pressure volume work, right? So you know those things about enthalpy. Okay, good. What we're going to do next is learn more things about enthalpy. Okay, so let's learn some more truths about enthalpy that we need to have. We need to understand these truths about enthalpy, and we'll take them one at a time. Enthalpy is an extensive property. Enthalpy for a reaction in the forward is the same number, but different sign for the reverse. And enthalpy for a reaction depends on the states. Now, we haven't paid too much attention to states, but we need to now. So let's take the first one. Enthalpy is extensive. Do you guys remember what extensive was? Woo, way back, chapter 2. Intensive, extensive properties. What's extensive? Do you remember? Oh, matters how much yes, it matters how much we have. Okay, it matters on the amount. So extensive means it matters how much we have. Okay, the more mass we have, then that's the property that changes. That depends. So enthalpy is it matters how much you have. So enthalpy is extensive. It matters how much you have. Now this is an example of a thermochemical equation. This is how we're going to write our thermochemical equations. We're going to have to specify the state now. Okay, so we're going to specify the state with a thermochemical equation. And then over to the right, we're going to put this delta H. That's the change in enthalpy that has occurred in this reaction. And we're going to write it out to the side, and usually we'll do kilojoules because a joule is so small. So we'll do kilojoules, and we'll have a sign in front of it. What's that negative sign telling you this is? Exothermic. That meant heat did what? Went out to the surroundings. Yeah, exactly. Left the system, right? Okay, so this is examples of a thermochemical equation. Now, enthalpy is extensive. It means it matters how much you have. My son decided he would bake a cake for his great-grandmother. She was 96 years old. So he thought, oh, wouldn't it be fun if we put 96 candles on the cake? It's like, oh, you forgot that enthalpy was extensive. Okay, because one candle gives off so much heat. But what would 96 candles do? Oh my gosh, the thing was giving off so much heat, the icing was starting to boil, and all the candles were all melting from the heat, and it was just a mess. Okay, so it matters. Enthalpy is extensive. So that's why when you get to be really old, you have a 9 and a 6. Yeah, there's no 96 candles. There's a reason for that. And it's because it's extensive. All right, so tell me, what do you think is the difference between these two equations? Okay, so you're saying we have what? Twice as much ammonia produced? Okay, so what does that mean? Twice the enthalpy, right? That makes sense. If I have 96 candles, that's 96 times that one candle, right? So if I had twice as much ammonia produced, wouldn't that give me twice as much enthalpy? Yeah, because it matters how much you have. So this amount, this 91.8 kilojoules, refers to producing 2 moles of ammonia. If I double the ammonia, I'm going to double that number. If I triple the ammonia, what am I going to do? triple that number, right? If I halve the ammonia, what am I going to do to the number? Half it, right? Does that make sense? Okay, so this number is tied to 2 moles of ammonia. This number, you could say, is also tied to 3 moles of hydrogen. If I doubled the moles of hydrogen, what's going to happen to that number? I double it, right? And then this number also could be referred to 1 mole of nitrogen. Okay, so I can use that number for any one of those. But it's tied to the coefficients, isn't it? Oh, how about that? Isn't that a relationship? Yeah, true and valid relationship, isn't it? Yes, it is. The negative 91.8 kilojoules is to 2 moles of ammonia. Or negative 91.8 kilojoules is to 3 moles of hydrogen. Or negative 91.8 kilojoules is to 1 mole of nitrogen. Does everybody see that? And then this number, minus 183.6 kilojoules, well, that refers to 4 moles of ammonia, doesn't it? And then this same number also refers to 6 moles of hydrogen. And then that number refers to 2 moles of nitrogen. It matters how much you have. Enthalpy is extensive. All right, that's one of the truths. Let's do another one. How about forward and reverse? Okay, what's going on with these two? What's the difference between these two? They're different? How are they different? Oh, products became the reactants? And what happened to the reactants? They became the product. So did we reverse that? Yeah, we reversed the reaction. Okay, this is the way it was, and then we reversed it. The products became the reactants, and the reactants became the products. We reversed it. So it's kind of like we took this reaction and we flipped it. So if I say that we flipped a reaction, does everybody understand what that means? Can I use the term flip the reaction? Are we good with that? So here's the reaction, and we flipped it. That means we reversed it. Is that okay? All right, so if I say flip the reaction, you know what I mean. Now, what happens when we flip the reaction? The sign changed. But did the number change? No. That's like saying, hey, I've got a boulder here, and it's going to roll down. Okay, there's a certain distance. It rolls down, energy's released. But I have to get the boulder back up. Energy, I got to put energy in, but it's still the same distance. Okay, so, yeah, it's still the same number. But what happened to the sign? Changes. Okay. So we have to remember all these truths because we're going to actually use them. We're going to use them to do stuff. Yes. All right, and then the last one is it depends on the state. What do you mean it depends on the state? What happened? What's the difference between these two? Okay, so we see a difference here. One's a liquid and one's a gas. So if I have liquid water and I want to change it to the gaseous state, what do I have to do? Do I have to add heat, take away heat? What have I got to do? Wait, add heat, right? Okay, so I've got liquid water and I want to heat it up. I have to add heat. All right, well, let's see what happens. I have to add heat. So I have to get the heat. I have to use some of the heat, right? So this first reaction is a minus 571.6 kilojoules, but the next one's a minus 483.6 kilojoules. Why is it less? One is the gas. So the gas one is less. Why is it less then? Because I had to change it to a gas. And I'm going to have to use some of that heat? Yeah, I have to use some of that heat to change the liquid to a gas. So that's why the enthalpy is different. So the enthalpy for this reaction is very different from the enthalpy of that reaction. And the only change is the change of state. So we do have to pay attention and specify our states because change of state does matter. Okay, so we got the three truths, right? First one, enthalpy is what? Extensive. What does extensive mean? Matters how much you have, right? It was very much tied to those moles, weren't they? Those coefficients. Okay, and the next one, what did we say what happens when we're flipping? What did we say? Reverse the sign. Do we change the number? No, just reverse the sign. And then the third one, enthalpy is what? It's dependent on the state. Perfect. Okay, those are the truths of enthalpy. So now that we know lots of truths about enthalpy, okay, and we know that we have this enthalpy here that's related to the coefficients, wow. Does that mean we could do something like, say, stoichiometry? Yes, we can. Yay. And you thought we were done. It's back. It's back. We never get rid of it. We're always using it. Okay. Yep. 1412 too, by the way. We're going to use stoichiometry. Yeah, you're like, oh boy, that'll be fun. Okay, so it's back, yes, but we know how to do stoichiometry, right? We can do that. And we were sighing. I was like, oh no. Yeah. Okay. Well, this will be easy. This stoichiometry with enthalpy is very, very easy. Okay, because instead of really doing that mole to mole ratio, we're going to change that and we're going to say mole to heat. So that's pretty much all we're going to do is do the mole to heat. Because when we get to heat, we're pretty much there. So for example, calculate the grams of nitrogen should be used to produce 1,250 kilojoules of heat. So let's put that up there and I'll show you how that's done. I'm going to start off with my given, which is the 1,250 kilojoules of heat. The 1,250 kilojoules heat is produced, right? So wouldn't that be a negative 1,250? Negative 1,250 kilojoules of heat, because producing, that means exiting the system, which means it's going to be negative, right? Okay, so I'm going to write that negative number down. Now, I'm going to do a mole to heat ratio instead of a mole to mole. So, we know, where am I going to get the mole to heat ratio from? The equation. And in this case, what are we looking for? We're looking for nitrogen. So I'm going to say enthalpy compared to what? Nitrogen, which is over here, right? Okay, there's my mole to heat. All right, now let's set up our dimensional analysis. And if you know, if we have kilojoules on top, guess what goes on the bottom? Kilojoules. And we're doing a mole to heat. And we're talking about moles of nitrogen. Isn't that what we're looking for? Okay, so I'm going to write moles of nitrogen. Now, you know where I'm getting these numbers from, right? Where do these numbers come from? Balanced equation. Okay, so can we write those in? What would this enthalpy be? That's what? Negative 91.8. Now, what would the moles of nitrogen be? 1. Does everybody see where you got that from? Okay, units cancel. Yay! So I have to divide by the 91.8, not multiply by. All right, and it is a negative. That's true. But you know what? The negative and the negative cancel out, don't they? So it's going to come out to be positive, which is good because mass can't really be negative. All right, now we want to go for what the problem wants. So we want it in what units? Grams. How am I going to go from moles to grams? Molar mass. There you go. If I've got moles of nitrogen on top, what goes on the bottom? Moles of nitrogen. And I'm trying to change that to grams of nitrogen. And we get that from periodic table. So it's N2. So look at nitrogen. Yep, so it'd be 28. And where does the 28 go? With the grams or the moles? Grams. It's always grams in how many moles? 1. And my units cancel? Yep, so I'm multiplying by 28. Okay, and when I do that, my answer comes out to be 381. Perfect. Grams of nitrogen. There you go. Okay, see, that's easy. Just, that's easy. That's a little mole to heat. Okay, great. Now do the next one. Okay, you do that one. And this time you're trying to find the heat produced. So what are you going to start with here? What are we going to start with on the second one? 45. We're going to start with the 45 grams, right? Because we're trying to find the heat. And you're going to start with the 45 grams, right? And then you're going to do your conversion and do the mole to heat, right? Let's see. I think next weekend, yes.
Oh, next weekend. So it's not during the week next week.
No. They all fall on the weekend. So this weekend is test what? 2.
And that goes until what day? Monday.
Tuesday. We go Saturday to Tuesday. And then test 3 is when? Yeah, the next Saturday to Tuesday. And then test 4, next Saturday to Tuesday. And then test 5. I know.
Can we take it like in another campus? Like the campus?
What, is good ball open on Sunday?
No, but you know, if it's
Always. If you change bus routes halfway through. No. No.
Okay, so how are we doing? How are we doing on this one?
Do I have to count? Because I always use, like, the whole numbers. But, I mean, people usually use, like, 2.
This is better. You should.
Okay, so this is right?
Yeah, you should always use the whole number. It's better. It's better. It's not as good. It's not as good.
Okay.
You'll be a little bit off on your answer when you do that.
Yeah.
You don't want to be off on your answer, right? Okay, are we getting it? So you guys got it? Okay. How are we guys doing back here? You good? Yeah? What did you guys get? 544. 544. How about you guys? Good? Getting it? Okay. Easy, right? No problem, yeah? Okay. So everybody could do our stoichiometry with enthalpy. Okay, there you go. Awesome. All right. Yeah, okay. Oh. Yep. Yep. Got it, yeah. You got it? Tracy, is it making sense?
Negative times a negative is the positive.
Yes. That's it. You got it. Oh, you got that stoichiometry. It's so easy. It's so easy now. Look at you, just whipped it out.
What is the final answer?
What's that?
Final answer.
Oh, the final answer? 544, 1 or 0 point something. Yeah. Okay, what did we get for the answer then? What'd you guys get? 5440. Did everybody get 5440.5 or 5441?
I got
5441.
But the sign minus.
Oh, no. Wait. You're right. It is a minus. It is a minus. The first one canceled out. The minuses did the first one, but not the second one. Because 45 grams, you can't have a negative mass. All right, so you're right. It is minus. So did everybody get minus? Okay, the first one, the minus is canceled out, but not the second one, right? Okay, so far we've talked about enthalpy and we've used it, didn't we? Yay, we've talked about enthalpy and we've used enthalpy in a stoichiometry equation. Yeah, that's easy. Okay, well, the next question is hey, how do we get that number? I mean, you used it, but how do you get that number? How do we measure that? How do we come up with that? Okay, so that's the next part. The rest of this chapter, actually, in chapter 5, is going to be talking about, hey, how did you get that number? We're going to do it 3 ways. We're going to talk about 3 ways. First way is calorimetry. It's experimental. You're going to actually do an experimental data, and you're going to come up with that number. That's over to the right side of those equations. That's how you're going to get that. We've used that number. Now we've got to talk about how we're going to get it. Okay, so and calorimetry is 1. Then we're going to use Hess's law. Okay, Hess's law is fun. I think it's like puzzles. It's always fun. And then the third one, which is not hard, but it's called heats of formation. Okay, so those are the 3 ways that we're going to get that enthalpy, and that's what we're going to spend the rest of chapter 5 really pretty much talking about. Okay, so this is a good time for a break, and we'll come back and we'll do that. All right, so let's be back at 1.
I'm going to get a pop.